So this next chapter we're going to talk about rotational or circular motion, and basically everything in physics that's introduced is introduced to make life easier. And if we wanted to talk about rotational things that go in circles in linear terms, we could do, but the problem is that it wouldn't work out, it wouldn't be as easy to think about, etc. And the reason why we care about rotational stuff is because we get some very amazing effects. And I can show you one of the very amazing effects using this little machine here. So this is very heavy. It's actually, I didn't realize this flashlight had the heaviest one in. So we take this. This is just a winding up device. Put it in here. Sorry, put it in that way. And then we just wind it up. And I need some help. Can you do like that? Sure. Do you want to pull or do you want to hold? Okay, so hold on to this, 2 hands. So, first of all, I'd like you just to turn it like that. Pretty easy, yeah? Pretty easy. All right, let's turn it back again. And then what I'm going to do is, I'm going to take this same wheel and just make it have some rotational motion. Now, try and turn it.
Yeah, that's pretty good.
It's just completely different. It's like...
Stay steady. It's like...
Yes. It's so heavy. Do you want to have a go? No? Do you want to have a go? And this is a gyroscopic effect. When you get in a plane and they fly across the country, these days they use GPS to find their way. But before GPS, they would use gyroscopes to keep the plane pointed. Not a compass. They wouldn't use a compass because the Earth's magnetic field is too ununiform. So they'd set up their gyroscopes and they'd point towards like Chicago. And then whenever the plane turned, they could know where Chicago was by the direction. So you get stuff like this, thank you. Anybody else want to have a go? I'll leave it here so we can play with it before you leave. It's a bit heavy, just be careful about this. And this is the wheel that you started off with. So we get some fascinating mechanical effects with circular motion. And it turns out also that a lot of the mathematics that in general physics they develop for circular motion is actually incredibly useful for waves. And so and waves are everywhere. Light is a wave, sound is a wave, electricity is a wave. So this section becomes really useful in general physics. So here's 2 pictures of the same thing. One of them is showing, if you like, a traditional way of looking at circular motion where, in fact, what I'm going to do, yeah, I can actually. Oh, that's very interesting, I can. Have I got a pen? Don't think I got a pen, that's the only thing, okay. Just follow my little dot thing. So here we have tangential speeds. The bit on the outside goes fastest, the bit on the inside goes less fast. The problem is that every point on this radius has a different tangential speed. So trying to calculate anything becomes totally arduous. It turns out that if I redefine this in terms of circular motion, every point on this goes through the same angle. So it all has the same angular displacement, although it's got different tangential displacement. It goes through the same angle in the same time. So it's got the same angular speed, whereas the tangential speeds are all different. And if it's speeding up or slowing down, it's got the same tangential acceleration, even though the angular accelerations are all different. So what is a real mess if we try and do it in linear terms becomes very simple in angular terms. The trade-off is we have to invent some new symbols because we've run out of symbols. So we start using Greek letters and it makes everybody feel uncomfortable. You're not alone if it makes you feel uncomfortable. Everybody feels uncomfortable with it, but you get used to them. So this little W, this curly W, is called an omega. And it's just the symbol we use for the angular speed. There's not that many of them, but there's a few of them. So we're going to talk about that. We're going to talk about, and then the other thing that's kind of interesting that I'd like you to have a taste of is, although we are used to talking about angles in terms of degrees, it's completely made up. If a space alien came down, they would not talk in terms of degrees. Why 360 degrees? It's just made up. But they would talk in terms of radians. A radian is like a big degree. A radian is about 60 degrees. And it comes naturally out of the geometry of a circle. Unfortunately, there's not a whole number of radians in a circle. So people tend to shy away from it. It's a bit big. 60 degrees having one radian is a bit big. And it's not a whole number when you go around a circle. So people tend to prefer the degree. But they're just two numbers. So I'd like you to at least get a taste for the radian. So it doesn't sort of make you feel bad. And then we're going to start talking about objects and spinning objects. And the weirdest thing happens. And I can show you that as well if I just nip to the back for a second. Did I bring them out? I thought I brought them out. Can I have these two guys here? So, first of all, hold them like this and tell me. I'll go by the handles, just in the middle. Hold them in the middle. And then tell me. Don't jiggle them. But they feel about the same weight, don't they? Yes. They feel about the same weight. If he jiggles them, you can tell they're not. But you can tell that there's something odd going on. They are the same weight. Now, I'd like you to try and jiggle them as fast as you can. And what do you notice? It's lighter. And it's actually not. It's the same weight. But what it is that this one has the weight in a different position to this one. Okay? You want to actually try it from the end and try doing that. You might just yeah. Again, the red one is easy, isn't it? Thank you. Do you want to have a go? Do you want to have a go? Nah, come on. Do you want to have a go? So I'm going to swap them. So just hold them in by the handles and just about the same way. Okay? Now, it's amazing, isn't it? There's just like a huge difference. That red one, you can see is doing it much easier, yeah? And yet it's the same way. And you can see, I can show you, if you look, you can't see through that hole, but you can see through that hole. You can see through that hole and you can't see that hole. All they do is they took the mass and they moved it to the middle. So the middle is by your hand, and here it's a long way away. And that in itself is just an amazing thing. So an object's willingness to rotate depends upon its positioning of its masses. If I were to take this wheel and move those masses to the middle, it would spin a lot easier. Because they're outside, it spins quite reluctantly. It starts spinning and it stops spinning quite reluctantly. And this crops up, so we get this situation like here where we say, well, the turning effect, if the masses are far away from the axis, it has a more inertia than if it's near the axis. Take a pencil. If you imagine spinning the pencil around the axis, it's easy. If you imagine spinning it around its middle, it's harder. If you imagine trying to spin the pencil around its end, it's even harder. And that's why when you throw something, it tends to rotate about its center of mass. Because the center of mass is the middle point for all the mass distribution. And so when you spin about your center of your mass, you've reduced your moment of inertia. So I want to talk to you about rotational inertia. I'm going to talk to you about intuitively how you know some of these things. You're walking on a wall and you start feeling uncertain. What do you do? If you feel like you're going to fall, what would I do?
Get lower.
I could get lower, yeah. What's the instinctive thing you do when you put your arms out, don't you? Then you go like that, yeah? To balance. What you're really doing is you're moving more mass away from your turning axis. Falling over is rotating about your feet. That's what falling over is. By bringing more mass away from my turning axis, I make my moment of inertia, my rotational inertia higher, which means I'm more stable. So it means that intuitively, you want to bunt, I think it's called. And with bunting, you want to make sure you hit the ball, yeah, because it's not going to go very far. So you just want to, so you hold the bat halfway down, so you can move it very quickly. When you want to really hit it out of the park, you hold it by the end of the handle, and it's not as easy to change where it's going to go. So you're guessing a bit more, but you know you can get more force behind it. But you want to bunt, so you just want to, wherever it goes, I'm going to get it. You reduce that distance. You bring the mass more symmetrically about your hand. You go to Cirque du Soleil, you see these guys walking on these tight ropes. You have this big pole. Why on earth are they carrying a pole? They're carrying a pole because if they start feeling, imagine not putting your arms out, put something heavy in your arms. So I'm even more stable. If I'm feeling unstable, if I do that, I've not only got the mass of my arms, I've got the mass of these guys. So I put it together as a thing, and now, oh, I'm really stable. We applaud them like crazy. But they've got this big pole that's probably making them walk. It's like walking down a sidewalk for them. Probably isn't, but it's a lot less difficult than we might think. And then the last little thing is, and this kind of gets me, is if you take a tall person and you say, just swing your leg backwards and forwards, just like, not forcing it, but just like natural, close your eyes, do natural frequency. Whatever feels comfortable. And then you get somebody who's short and you get them to do that. What you notice is the person who's short has a higher natural frequency than the person who's long. And that's why you can have a really tall person and a really short person, and they can actually walk together quite naturally, because the little person's taking more little steps, and the big person, because they've got big long legs, is taking slower, big strides, and it kind of balances itself out. So this kind of stuff comes up all throughout nature, and it's one of the more interesting parts of what we do. We'll have races, we'll do balancing, and we'll talk about talks. And we'll start this next time. Sorry, I kept you just a little bit.